So in this example problem, we're going to draw the shear diagram, or V. The shear is a function of x, and the moment diagram for our cantilever beam that's shown below. So in this example, we have a concentrated force of 2 kilonewtons that's applied at the end of our cantilever beam, and we have a distributed load that's applied 2 meters from the left-hand side of the beam to the support at point B, which is a fixed support. So our first step in order to draw our shear and moment diagrams for this example is we need to determine our reaction forces at point B. Alright, so we're going to draw our free body diagram of our beam. Alright. We have 2 kilonewtons. Alright, we have 2 meters from the 2 kilonewton load until we have our distributed load, our constant distributed load along the length of our beam of 1.5 kilonewton meters. And then on the right hand side of the beam at point B, we have our three forces. We have our reaction due to, in the y direction, we have our reaction in the x direction, and we have our couple moment due to the fixed support. All right. So we want to find MB, BX, and BY. In order to do that, we're going to apply our equilibrium equations. So the first thing we'll do is we'll sum all of our forces along the x direction and set that equal to 0. In this case, the only force we have in the x direction is we have B of x. Alright, therefore B of x is going to be equal to 0. Alright, the next one we can apply here is we can sum all of our forces in the y direction and set that equal to 0. If we do that, we will get minus 2 kilonewtons minus 1.5 kilonewtons per meter times the length, in this case it's 2 meters, plus B of y. So you get from that, you would say that B of y would be equal to 2 kilonewtons plus 3 kilonewtons, or 5 kilonewtons. Right, and then the last thing we would do is we would sum all of our moments about point B and set that equal to 0. If we did that, we would get 2 kilonewtons times 4 meters plus 1.5 kilonewton meters times 2 meters. Alright, so that's our equivalent concentrated force due to the distributed load times the distance to the centroid of the distributed load. Since it's a constant distributed load that will occur in the center of the distributed load, so the moment arm in this case, xc, is just going to be equal to 1 meter. Alright, and then we have plus m of b. So we will say that m of b is going to be equal to negative 8 newton meters plus negative 3 kilonewton meters, so we'll get minus 11 kilonewton meters, which is going in the clockwise direction. Okay. All right. Alright, so once we have this information, we can now start directly drawing our shear moment diagram. So we're just going to start with the shear diagram first. So for our shear diagram, what we're going to do is we're going to say we have our positive shear, we're going to have our negative shear, and then we'll have 0. Alright. And then we'll have on the and then on we'll have our x-axis. Our x-axis will be the length of the beam. So we'll draw, let's say x is equal to 0 on the left-hand side. We'll have x is equal to 2 meters in the center here. And we'll have x is equal to 4 meters at the end. Alright. And then, so this will be in units of kilonewtons. Okay. So what we're going to do is we're just going to look at our free body diagram. So using our free body diagram, we know at point B we have a applied load, or sorry, at point A we have an applied load of 2 kilonewtons. Okay. So we're going to say, so this is our 2 kilonewton force that's applied at point A. Alright. And then along, so this is due, so then along the, from point A to 2 meters away, we have no applied load. So our shear force would not change along this region. Alright, so V of x is constant along this point. Alright, and then from 2 meters to the end of the beam, we know that V of x is going to be equal to the integral of, or I should say, that delta V is going to be integral from 2 meters to 4 meters of W of x dx. Alright, so from 0 to 2 meters, we know V of x is just equal to minus 2 kilonewtons. Alright, and then from the rest of it, or from 2 meters to 4 meters, we know it's going to be equal to minus 2 kilonewtons plus delta V. Alright, so in this case, we would substitute, it would be equal to minus 2 kilonewtons plus the integral of 2 meters to 4 meters W of x dx. So W of x dx, W of x we know is a constant. It's equal to minus 1.5 kilonewtons per meter times, and that's it. It's a constant number, dx. All right. So if after we integrate that, we will get minus 2 kilonewtons. And then what I'm going to do here is, instead of saying from 2 meters to 4 meters, I should have wrote just x. So 2 meters to x, or wherever we want to stop this section. So we'll end up getting, in that case, we'll get minus 1.5 kilonewtons per meter, which is just a constant, times x minus 1.5 kilonewtons per meter times 2 meters. All right? Or we can write this whole thing as just being equal to minus 1.5 kilonewtons per meter times x minus 2 kilonewtons. All right? So what we end up getting here is we just have a slope of minus 1.5 kilonewtons per meter along this section. All right, so what we end up getting is we'll get a straight line, all right, with this equation. All right. All right, and then at the right hand side, we have another, if we look at our free body diagram, we have another concentrated load, which is B of y. All right, and that's equal to 5 kilonewton meters. 5 kilonewtons, sorry. All right. So this is our shear diagram here. So using our shear diagram now, we can then draw our moment diagram. So our next step will be to draw our moment diagram. So when we draw our moment diagram, right, it's going to be a little bit odd looking because our clockwise or our negative moments will be going on, will be on the top, and then our counterclockwise moments or our positive moments will be on the bottom of our diagram. We'll still have x is equal to 0, we'll have x is equal to 2 meters, and we'll have x is equal to 4 meters on our diagram. Alright, and then we will have, so we know that our change in our moment is going to be equal to the integral between our 2 points. So in this case, we'll have 0 and x for between 0 and 2 meters, and then we will have v of x along that point dx. So v of x from 0 to 2 meters was just equal to minus 2 kilonewtons. So our delta m would be equal to minus 2 kilonewtons x minus 0. Alright. So it's going to be equal to minus 2 kilonewtons times x. Alright, so that will look like just a, I'm going to redraw our x-axis here just to make our lives a little easier. So at the far end of the beam there's no couple moment, so it'll start at 0, and we'll just have a straight line of minus 2 kilonewtons x till we get to 2 meters. Alright, then after that point we will say delta m is going to be from 2 meters to the rest of the beam would be equal to v of x along that section. Alright, time, which is we defined as being equal to minus 1.5 kilonewtons per meter times x minus 2 kilonewtons dx. Alright, so so if we do that and we integrate, what we'll end up getting is we'll get delta, or we'll get delta m is going to be equal to minus 1.5 kilonewtons per meter times x minus 2 minus 2 kilonewtons. There's a x minus 2 squared, I should say, and then, sorry, this should be minus 0.75 kilonewtons, and then this would be minus 2 kilonewtons times x. Right. So this would be our m of x. Along the second part of our section. Alright, so this is going to be a polynomial. Alright, and then it has a negative coefficient in front of it, so it'll be look something like this. Alright, And then at the very end of our beam at 4 meters, we have an applied concentrated load M of B that was equal to 11 kilonewton meters minus 11 kilonewton meters, which is in the clockwise direction. All right, so it would be added at the very end. All right, and that concludes how you draw your shear and moment diagrams for this example problem. So just to recap real quick, the first thing we did in this problem is we found the reaction forces at our supports. So at point B is a fixed support, so we need to find B of y, B of x, and M of b using our equilibrium equations. Once we had all of our support reactions, we should be able to draw our shear diagram using our free body diagram that we drew at point 1 with our known reaction forces. So we knew that our shear force should be constant after our concentrated force is applied, and then from 2 meters to 4 meters, our slope is going to be equal to, or V of x would be equal to the value of the shear force at 2 meters plus the change in V along the direction. So when we did that, we ended up getting V of x is equal to minus 1.5 kilonewton meters times x minus 2 minus 2 kilonewtons. And then we can draw our shear moment diagram, and we just have to integrate the functions that we had originally solved for in the first part of the problem, and include, in addition to those integrations, you have to include the effects of any couple moments, and in this case the only couple moment was applied at the support on the right hand side. So that concludes this problem, and then we'll do one more example problem on shear and moment diagrams.